A finite state automaton, an FSA, is defined with 5 properties. The first one, A, is the alphabet. So what symbols can we use in this finite state automaton? In this situation, it's only 0 and 1. So if we are in a state, we can do something with a 0 or we can receive a 1, and those are the only possibilities. The second one, S, is the set of possible states. So in this example, that would be S1 and S0. Then the third one, Y, would be the possible finalizing states, end states. So when is this word allowed to stop? And in this case, that's only S1. And then, of course, S0 would be the initial state. Then we have one left, that's the F. And this F is the state table. It's the function which defines if we are in a specific state, what will happen when I receive a 0, or what will happen if I receive a 1. So the state table is given like this. If we are in state S0 and we receive a 1, we stay in S0. If we are in state S1 and we receive a 1, we go to S0. So a state table defines the transitions from one state to another based on the received symbols. Okay, let's look if we can take it the opposite around. So we have an alphabet, we have states, we have an ending state, initial state, and a function. Okay, let us try to draw the corresponding graph. So we have 3 states, S0, S1, and S2. The initial state is S0, so we start from this state. I have 2 final states, which is S0, so we have a double circle here, and S1. Okay, then let's look at our function table. So if I'm in state S0 and I get an A, I stay in S0. If I'm in S0 and I get a B, I go to S1. If I'm in S1 and I get an A, I go back to S0. And if I'm in S1 and I get a B, I move on to S2. Then the last row, if I'm in S2 and I get an A, I stay in S2. And if I'm in S2 and I get a B, I also stay in S2. So this would be the corresponding graph with the finite state automation with the help of the 5 properties which define the FSA. Okay, we've just drawn a graph of a finite state automaton. Now let's see if the words given here, W1, W2 and W3, are part of the language generated with the finite state automaton. Okay, let's look at the first one, W1. We start with an A, okay, that's good, we stay in S0. Then we get a B, so we go to S1. Then again we get an A, so we go back to S0. We get a B, so we go to S1. We get another B, we go to S2, and we get an A, and we are still in S2. So, is that word acceptable with its finite state automaton? And the answer would be no, because we're ending in S2. And S2 is not a final state, so this is not allowed. The second one, okay, W2. We start with a B, so we go to S1. Then we get an A, we go back. We get an A, we stay in S0. And we have a B, so we go to S1. And indeed, this is a final state, so this is a perfect word with this finite state automaton. Then the last one, does the empty word belong to the language? And then of course we know, because the starting point is in S0, and the S0 is also part of our final states. So if this is the situation, then lambda is always part of the language. Let's look at another FSA. So we have a starting position in S0. We have 2 symbols. So the alphabet would be AB. We have two end states, so S would be S0 and S1, and we have a transition given by the arrows. Okay, let's first make a regular expression of this one. And now you see we have one initial state, but we have two possible ending states. So that means we have two possibilities. We can start in S0 and then finalize in S1, or we can start in S0 and finalize in S0. Okay, let's look at the first one first. So we start in S0 and we end in S1. So we start with an A and now we can finish if we like. But we can also return to S0 with A or B. And then we have to go back to S1 again. This can be repeated as often as we like. So from S0 to S1, we minimum need one letter, A, and then we can go back with A or B and go up again with an A. Or we can have the second road. So we can start in S0 and end in S0. And because we can do nothing at all, because the first state is also a possible finalizing state, we can have the lambda word inside. So that means we have now to repeat with a star, so to be possible to have nothing at all. Okay, so we can go up with A, we can go back again with A or B. And this complete cycle can be repeated as often as we like. So the regular expression in total would be A followed with A or B A star, or, and then between brackets, A or B, and that all combined star. Well, is this graph a finite state automaton? Well, no, it's not. Because if we look at S1, for instance, we can go back with A and B. But if we look at S0 and I get a B, I have nowhere to go. And there is no define from S0 to SB. So how can we fix this? Okay, how can we fix this? Well, a nice solution would be to add a sink, a so-called sink. So for every symbol where there's no definition of the state transition, we add a sink. So in this case, if we receive in S0 a B, which is not allowed, we'll just sort of drain it. We say, okay, if we get a B in this situation, you go to a sink and I never want to hear from you again. So whatever you get here, whether it's an A or a B, you stay in this sink. So symbolically, we added a sink. So if in S0 we get a B, we can never get out of this finite state automaton anymore. If we look at another example, then this is one with three states, S0, S1, S2. We have one finalizing state. The alphabet is X, Y, and Z, and we have this entry point. So let's see if we can make a regular expression of it. So we start from S0 and we can get an X or a Y or a Z. Okay, then we are in state S1 and we could finish. But we don't have to. So from this point we can continue, if we like, by taking an X, going to S2 and having an Y to return. And this can be repeated as often as we like. So the corresponding regular expression would be start with an X or a Y or a Z and finalize with as many XY cycles as we like. So the shortest word, for instance, in this FSA would be an X or a Y or a Z. But we could also have X, XY or Z, XY, XY. Does lambda belong to this language, by the way? No, that's not so, because we have to start with minimal one real symbol from the alphabet.